In many ways, optimization can be related to related rates. So it basically just makes use of what we've already learned and puts it in a practical setting. So as I said here, is how we make use of extrema found through differentiation. So if you're trying to find the maximum volume, then you already know how to find the maximum based on the last unit. And if you're trying to find the minimum cost, it's just the same thing. So as you would with anything else, you're going to just solve it like an extrema problem. It's just with an application that would be used in the real world. So don't overthink it, and just like with related rates, always draw a picture. So I have some example problems here, and they're based off of problems that you will see pretty frequently. And they're pretty basic, but you will still see them a lot, so it's good to know how to do them. So here we have a box that will be made from a 40 by 40 inch piece of cardboard, and the corners will be cut out so the sides can fold up. And what dimensions will maximize the volume, and what is that volume? So I've drawn the picture here. This is our 40 by 40 piece of cardboard, and it said that you will be cutting out the corners. So I have cut out the corners here, and I have denoted this distance here as x, which will be the height of our box later on. And if you draw the picture, it makes sense visually why that would work. And then of course for the lengths of the sides, this is a square, so they're going to be the same. But also, it will be 40 minus 2x, because this distance here, which is x, will be cut out. And so you'll have 40 minus 2x for both the length and the width. So now knowing that, we have our volume, which would be just length times width times height. And if we have the length and the width both equaling 40 minus 2x, we can set those to be 40 minus 2x squared, since they'll be multiplied by each other. And as previously mentioned, the x will be the height. So this is our volume equation, and I just went and simplified it. And if you want to see that in detail, you can just pause the video here. And so now that we've reached this simplified version of the equation, you know that you want to maximize this because it says what dimensions will maximize the volume of the box. So we will differentiate and then set that equal to 0. And I factored out a 4 here to make it a little bit easier. And when you solve for 0, or solve for x when it equals 0, you will get x equals 20 or x equals 20 over 3. So since we have two answers, you should do this anyway, but if you have two answers, you have to check which is the maximum, which is a minimum, or if they're both maximums, or, you know, you should always check. And so I've done a little sign chart here, which shows that 20 divided by 3 is the maximum because the derivative is increasing, or sorry, is positive as it is approaching 20 divided by 3 and negative after that. So then, knowing that, we can solve for the other dimensions, and you get 40 minus 2x with x substituted for being 20 divided by 3. So you would get 80 over 3, and that is both the length and the width, as I have put here. And then you multiply all those together to get your volume, which would be about 128,000 over 3, or approximately equal to 4,740.74 inches cubed. And units are always very, very important in problems like this. If they're not given, it's good to write like units cubed or something like that, just to cover all your bases. And here's another simple problem. I'll try and not cut into the other one. I should have left a little bit more space here. But given a problem like this, it says the Smiths are fencing in their backyard. They have 60 feet of fencing material. What is the maximum area that they can fence in if one side of the rectangle is along the side of the house? So that's basically saying that part of the perimeter is cut out, so it's no longer really the perimeter, but the distance here is what I have denoted as P, which again, it's not really the perimeter, but it works. So in order to find out which side doesn't need fencing, I have decided that if we're trying to minimize the cost, or rather, sorry, we're trying to maximize the area with the amount of fencing, so you don't want to put the fencing on the long side because that will not get you the maximum area. So I have said that the width here is W and the length here is L, so that we would get our perimeter equal to, usually if it was not with this side cut out, it would be 2W plus 2L. But since this L is covered by the house, this would just become L. And so then you can solve for either one because your area is what you're trying to maximize. And so I think in this case it'd be easier to solve for L. So then 60 minus 2W is equal to L. And then you can substitute that in here. So you get 60 minus 2W times W. And to make it simplified, you can just distribute. So you get 60W minus 2W squared. Differentiate dA dW, because it's with respect to the width. You get 60 minus 4W, and then as you would with any other problem, you're going to set it equal to 0, find the maximum, and there you go. Another really famous problem is the Norman window problem. I hate these. They suck. Basically, a Norman window is a rectangle with a semicircle across the top of it, and you are trying to find the maximum area of the window if the perimeter is 10 feet. So, in order to get our area equation, we have to combine the area of this rectangle with the area of this semicircle. So the area of the rectangle is pretty easy, it's just x times y, and the area of a circle is pi r squared. R in this case is 1/2 of x, because looking at the picture you can see that this distance is the same as this distance, just cut it in half to get the radius. And then also, because it's a semicircle, you have to divide the area by 2, so that is where this 1/2 comes from. So you should get 1/2 pi times 1/2 x squared. And you can go ahead and simplify this, as I've done here, to x times y plus 1/8 pi x squared. And then, because you have two variables here, we're going to want to find the, we're going to have to solve for either x or y based on this given perimeter. So the perimeter is equal to this whole distance here, which would be x plus y plus another y plus 1/2 pi x, because the circumference of a circle is of course pi d or 2 pi r, and since r is 1/2 x, your distance should be 1/2 pi x. And then I solved for y because that is the most simple one in this occasion, because there's only one y in the area equation as opposed to two x's that you'd have to substitute in twice for. So doing that, I just substituted in here, and here's where your algebra comes in. And then after differentiating, you should get this really lovely equation, and then set it equal to 0. So the main issue with Norman window problems is that because there's so many pi's and fractions and things like that, some people get really confused. And in this case, it's the algebra that is the issue, as per usual, and not the calculus. And that's why these problems tend to be so difficult, because it's hard to make sure you don't like mess up this fraction here or mess up the answer later on when you're simplifying. So just be really careful with that. And as per usual, you just solve here. This is after setting it equal to 0. So then x, you should get 10 over 2 plus, I believe that is a 1/2 pi. Sorry, the pen is a little messy. And then I multiplied it by 2 over 2 so that it would be, there wouldn't be a fraction here. So yeah, that was 1/2. And this would be 20 over 4 plus pi.